Okay, so so the vector space corresponds. Every physical system corresponds to a vector space, and observables are division operators. Which again we will talk about. And then there's the Copenhagen Interpretation, which is very important in quantum mechanics. It tells you something about the probabilistic character of quantum mechanics. And very closely related, there's something called the Copenhagen Interpretation. We didn't talk much about this because it is an interpretation. It basically says that when you make an observation of a particular observable, essentially you collapse the wave function. Right? If the eigenstate of spin, for example, then you make an observation, then you will collapse the wave function. I'm going to talk about it as we come to that, but it's an interpretation, and people still debate it. And finally, we have dynamics. Right. So the Hilbert space is a framework, but the dynamics itself tells you that the time evolution of these vectors in the vector space is governed by the Schrodinger equation. So this is the state. I'm using the same symbol. This is the state. And its time derivative times an I is equal to something called the Hamiltonian. Which governs the physics of the system, or the physical properties. So if you have an atomic system, then you got to write down the right Hamiltonian to describe whatever atomic system you have. And so that's where the physics is. So today we're going to start with by systematically going through these principles. Like I said, it's going to take a good part of our semester. And for many of you, I'm guessing you've not really seen, or at least my experience, that physics students in Taiwan have not really seen a lot of these formalism. Right? Maybe bits and pieces of it. But really, by the time you've reached grad school, you really should have seen this at least once. Right, so this is the opportunity to do that. Okay, so let's begin. Right, so what's a vector space? So I'm going to be a little bit sloppy. I'm going to call sometimes it my vector space, call Hilbert space. Sometimes I'm going to call vector space. So we're going to start by first defining what a vector space is. And for that, I'm going to use some symbols. Actually, you've seen it already. And the symbol is this thing, the cat. Right? So so these symbols are called cats, or simply vectors, and in our quantum mechanical context are often called states. It's the physical state of the system, right? So for every physical system, is described fully, is fully described. vector space. Right? So there is a vector. So there's a Hilbert space, and the range of possibilities that your physical system can take is described by this Hilbert space. So therefore, at any given point of time, the Hilbert space, it's, the state it is in is described by some vector in the Hilbert space. But what the Hilbert space itself is that it obeys a bunch of rules. That's what it is. And there's a reason why it's called linear algebra. The linear part of it is quite important, as you will so soon see. So, the first set of axioms, so as you probably know, math is really just the subject of logic and reason. Right? So you have to start with some basic assumptions, which they call axioms. And from there, you deduce facts from that. Right? Depending on what assumptions you make, you'll get out different facts that follow. But so the first assumption is that to define a vector space, we're trying to answer this question. These cats have this property that when you add two cats or two states in the system, you get out another state. Right? So you won't ever find adding some two states together, you get something that completely is outside of this Hilbert space. Right? That's not the definition. The definition is that for and you can think of it in terms of our physical application here. Quantum mechanics says that if you have two possible states that your system can be in, they can be both. That means the same system can also be found in a superposition of these two guys. Right? So that's essentially what this axiom is saying. The math of it is that it's closed under addition. But the physics of it is that your system can be found in alpha, it can also be found in beta, but so can it be found in the superposition of these guys. Right? You have to normalize it properly, but otherwise that's basically what the axiom is saying. Now, it's also true that addition is commutative and associated. So what it means is that the order doesn't matter. Right? You can add alpha to beta, and you can add beta to alpha, and you can get the same. You will get the same result. Now, if we're talking about addition, it might look a little silly, right? Of course, addition is commutative, but if you are being strict about your mathematical logic, then sometimes the addition here may not mean the same addition we mean when we add numbers. Okay, so that's why there's a need to say this. But for our purposes, it will almost always be true that it's addition. Okay, and so it is quite easy to see that this definitely holds for our purposes. And then likewise, associativity means that it doesn't matter which order you add them. You can add alpha and beta, and then you add gamma, or you add beta and gamma, then you add alpha, and you have the same, give you the same result, right? And again, for most of our applications, it's just going to be addition, and it's quite obvious that it will hold. Okay. Now, for the second set of axioms, we need to talk about zero, right? So zero, of course, can correspond to the number, but zero in a vector space also corresponds to a vector that is essentially the additive identity, right? So by additive identity, it means the following. There is a vector called zero that firstly is obtained by basically multiplying 0, the number 0, to any vector. And it's called 0 because it's an additive identity in the sense that when you add it to any vector, so this is any vector, you get back itself. Okay. So meaning you first have to figure out, is there such a vector in the space that you're defining? And then secondly, does it really act as an additive identity? Right, so you can see, you add anything to it, you get back the same thing. So that's why we call it additive identity. And then, not only that, when you add, there is an inverse. Remember, it's an identity. So maybe I can remind you guys, for example, in matrix multiplication, when you have an inverse of a matrix. Okay, good. All right, and then we just need to now. So we figured out these guys. We need to figure out the 0 vector, but that's also easy enough. The 0 vector is just the vector with all the components 0. And we can also show that that is the additive inverse. So that's related to the additive inverse very easily by simply a direct calculation, right? So 0 is just a component, it's just an object with zeros in every component. Why? Because when you add 0 to anything, you're adding 0 plus W1, 0 plus W2, all the way to the D component. So that's of course nothing but W itself. So that's what satisfies the notion of being an additive identity. And then the inverse, the additive inverse is simply given by minus W. Okay, you need to identify what it is. And what is it? It's just the guy with the original vector, but with a minus sign in front of every component. And so why is that so? You can check, right? So you can check. For it to be an additive inverse, you need to add the blue with its additive inverse, and you need to get 0, the 0 vector. So you get W1, this is W1, minus W1, W2, minus W2, all the way to WD, minus WD. Just add component by component, and of course this is just 0. Okay. Now, that means we have verified this as well, and we have identified our additive inverse. So the only thing remaining is the multiplication over scalars, right? And so maybe I'll just summarize. This is axiom 2. These guys were axiom 1. And then finally we have axiom 3. So when you define a vector space, you need to tell people what these scalars are. And because we are now doing an example over the real d-dimensional space, our scalars, A, B, whatever you want to call them, they're all on the real line. Okay? So the slightly more general case will be to do it over d-dimensional complex vector spaces. Right? That will be slightly more general. And for what you will discover, I'll just mention it here. What you'll discover is that when you're dealing with discrete vector spaces, discrete finite dimensional vector spaces, Hilbert spaces, I'll explain this in due time, probably by next week. You will discover that basically all discrete finite dimensional vector spaces are basically CD, not RD, but CD, the complex version of what we're doing. Right? So what we're doing is already quite general. You just need to make it complex. Anyway, so if these are real, then A times W, for example, is going to be A times W1, W2, all the way to WD. And what is that? That's just the usual multiplication, component by component. So you have AW1, AW2, all the way to AWD. And so this is just saying that you get A times W. But A times W is obviously still a vector in RD. And therefore, we are okay. So it's closed under scalar multiplication. And then we just need to check that it distributes, right? So A times V plus W is, first step is A times V1 plus W1 all the way to BD plus WD. And then when you distribute inside, you get A times V1 plus W1 all the way to A times BD plus WD. And if you compare this with A times V plus A times W, what do you get? A times V is AV1 all the way to AVD, right? Plus A times W is AW1 all the way to AWD. But then you just add them component by component, and you get this. Right? So I don't think I need to do that. It's just addition, right? And so you do get that this is A times B plus W. And then the final one is the distribution over multiplication of scalars. So A plus B times W. Of course, you can work it out component by component. You have A plus B times W1, W2, and so on. So instead of A, you now have A plus B. But that's just the same, obviously, with A times W plus A times, maybe I'll write this way, right? So we have already shown, I think we've already shown over here, that you get A times W, right? So a sleeker way is to say that this is A plus B W, okay? And this, in turn, you can work out A times W plus A times B times W is what? Is actually just equals to AW plus BW and you can just add these two vectors, and so this is just AW plus BW, and you'll find that this is exactly the same thing, so therefore they are equal. Okay. So if you think it's quite boring, you're doing just fine, right? It's quite boring just because we're doing real d-dimensional space, and it should be boring because we are all very familiar with what is going on, right? But don't laugh at it because it's a warm-up. And what I meant to show you is a simple example of what you need to do to check whether your system is a vector space. Right? It needs to have a well-defined addition, well-defined multiplication, and you need to be working with scalars that are either real numbers or complex numbers, right? And you need to check it. So what you're going to do for your homework is to check for yourself that, in fact, the following examples, which are actually a little bit less trivial, less simple, you will check for yourself that these are vector spaces. Okay, so what are they? So for example, you will show that the set of polynomials with complex coefficients. Okay, and just the addition, the usual addition. Okay. It's also true, and it's going to be important for quantum mechanics, that the space of square integrable functions so what does it mean? So all f of x such that when you square the function and you take it, it is complex, you have to take the absolute value and then you integrate over all space. This is in fact an example of vector space. Actually, let's do it over d-dimensional space. So I will have d, I will integrate it over all the d-dimensional coordinates. Okay. Right, so you can integrate it, square it, and you can integrate it, and you get a finite number. That's what square integrable means. So that's a vector space, and you probably can recognize this is actually nothing but the wave function. But this is nothing but what is obeyed by the wave function. Because, I'm sorry, yeah, metric, yeah. I mean, I said the right words, but didn't write the right symbol. Yeah, so the wave function, because it's supposed to be a probabilistic, give you a probabilistic interpretation, must in fact integrate, when you square it and integrate over all space, it must in fact integrate 1. Right? So this is a special example of a square integrable function. Okay, and then also the space of homogeneous solutions. To ODEs, ordinary differential equations, or PDEs. Actually, I should say linear So what you discover is that what we call linear ODE and linear PDE, that linear is exactly the same kind of linearity that we are talking about for vector spaces. Okay, so you will discover this for yourself. And then finally, the other example that we have is that of matrices. So any space, any dimensional matrix n by n does not necessarily need to be equal to n, but the space of m by n matrices with complex entries, that will give you also a vector space. And let me just emphasize also that this is actually, we will soon see that the matrices that you are familiar with, I hope you're familiar with matrices, in fact, will find a connection to this more abstract version of linear algebra that we're doing. What you discover is that for finite dimensional discrete vector spaces, the matrices that you have seen before is actually nothing but a linear operator. Where there's a translation you can do. There's kind of a map. That's what mathematicians would like to say. There's a map between matrices and linear operators acting on the vector spaces. And we will see that more explicitly, but we'll have to wait a little bit. Okay, any questions for me? No questions? Who has seen this before? Who has seen this before? Who hasn't seen this before? Okay, good. If you haven't seen it before, that's good. So then you get some practice in your homework, and hopefully get familiar with it. I do want to warn, right? So if you're not familiar with more abstract stuff like this, you do need to practice, right? It takes some mental exercise to get familiar with abstract concepts. So this is what you will notice in my homework. Usually I'll give you guys a lot of homework. This is also why I don't give midterms and finals, right? Because I would prefer you just work hard during the semester. Don't get stressed out over just one midterm or one final. But the flip side is that you should, if you're serious about learning this stuff, you need to work it out for yourself and try to understand it. Particularly because if you get lost from the beginning, then it's very hard to catch up. Right? It's a whole structure, the whole logical structure. And don't wait until the next semester. Then you ask me what is a completeness relation? What's a cat? You know, that's even worse. What a bra? You know, that's even worse. So make sure. Again, it's for yourself, right? You're here to learn for yourself. Make sure that if you don't understand it, come and talk to me. Make sure you wrestle with it properly yourself as well. And ask questions. Yeah. Okay. So see you guys next Monday. Oh yeah, the first video has already been put up. If you go on the website, I already have linked. I decided to put it up on YouTube.